33% red, 33% green, and 33% of blue, then we can get perfect white light emission. Next. So generally, white light emission typically involves the mixing of three primary colors that I told you in the previous slides. Red, green, and blue are combining of two complementary colors. Means complementary colors means when you are mixing blue and green, you can get cyan color, which is coming around 475 nanometers. So if you are taking cyan color and this is a complementary color, and you are taking another primary color that is a red, then by mixing up complementary color and primary colors, you can get the white light emission. These are the possible applications of white light emitting materials in the field of LEDs lamp, because LEDs are mainly fabricated by the rare earth elements, are critical elements like indium, gallium, and these rare earth elements we don't have sources in our country. We are totally dependent on the China, which has exporting the rare earth elements for the LEDs fabrication, and these are the very costly. Also, we can explore these materials in the tunable dielasers. Tunable dielasers means by changing the concentration of one of the emitting pigments or any one of the emitting colors, we can tune this. We can explore this material in the tunable laser, flat panel display, and backlights. Next. Before going into detail, first I would like to introduce about how we can predict that this material gives the perfect white light. By calculating the CIE color temperature, CIE color coordinate and color temperature, we can predict that this material gives the perfect white light emission. When we are getting the X and Y, that is the chromaticity index, that is if it is coming about 0.33 and 0.33, then we can say this is the perfect white light emitting material. And from this color coordinate, we can calculate the color temperature. Every emitting sources have its color temperature. Nowadays, in the restaurants, people are changing the lights, LEDs lights. But if they are using the white LEDs, warm LEDs, cool LEDs, these warm, cool, and cool LEDs based on their color temperature. So from they are tuning this correlated color temperature, and color temperature around 500 Kelvin, that is the cool color. And if the color temperature is coming around 2700 to 3000 Kelvin, that is warm color. Yes. So this is the correlated color temperature. Well, if the correlated color temperature is coming around 7000 to 10,000 Kelvin, it is called daylight or natural color. And below to that, 4000 to 6000 Kelvin, that is the cool white light, and 1000 to 3000, that is the warm white light color temperature. Next. So in the literature, people are choosing the different types of material like inorganic, organic, nanomaterials, quantum dots, polymer, metal organic framework, inorganic or organic hybrids, metal complexes, and lignite material for the preparation of white light emitting materials. By applying the various photophysical principles, they are getting the white light emitting material by employing hydrogen bonding, mediated JTBs, and mixing of monomer and enzyme approaches. But in our approach is totally different what people have done earlier. That is, we are focusing on the preparation of fluorescent carbon-based nanomaterials for white light emission using a cost-effective and environmental benign approach. Next. So why we have chosen the carbon nanomaterials? Because carbon nanomaterials are very cost. We can prepare these materials in a very cost-effective and environmental benign process. They have very small size in the range of 1 to 10 nanometer, and these nanomaterials can be prepared by using two techniques like bottom-up and top-down approaches, applying various different types of synthesis approaches. Next. This is the possible application of fluorescent carbon nanomaterials for the metal-based quantum dots and organic dyes like excitation-dependent emission. As we see, as we change the excitation between 450 to 450 to when we are changing the excitation pattern, there is change in the fluorescence spectra, emission intensity. This is the very important phenomena. But organic dyes emits if you, whatever the excitation wavelength, organic dyes have a fixed emission, but in case of nanomaterials, we can change its fluorescence properties and high water solubility, excellent photostability, easy surface functionalization, good biocompatibility, and low toxicity. These are the multifunction These are the multifunction application of fluorescent carbon quantum dots in the field of drug delivery, optronics, catalysis, sensors, theranostics, and bioenergy. Next. So this is we have prepared white light emitting graphene quantum dots from coal soot, and we have filed Indian patent for that. We have in the literature most of the report examples was achieved white light emission by mixing of red, green, and blue. As I told you previously, are complementary color. Then the first time we have prepared white light emitting graphene quantum dot from coal soot from a single source and single material. We did not use red, green, and blue for mixing, and the developed process aids in the value addition and gain full utilization of coal soot based for the production of white light emitting material. So we have taken the 1 milligram of coal soot, and this coal soot we have collected in our department from anthracite coal, and then we have burned this coal and collected the coal soot in the glass plates. And then after this coal soot, we have mixed this coal soot with ethylene diamine of 10 ml and ultrasonicated at 2 minutes for room temperature. Then we have get the reaction mixture of ethylene diamine, functionalized this graphene quantum dots, and then we have centrifuged this reaction mixture at 7000 rpm for 10 minutes. We have found the graphene quantum dots. This is the visible light. In the normal light, we have obtained the Ellis color of graphene quantum dots. We have not only focused on the ethylene diamine, we have explored this graphene quantum coal soot in the various solvents like H2O, ethanol, THF, DMF, DMSO, and ethylene diamine. But we did not see any white light emission in the case of H2O, ethanol, and THF because of in this solvent we are getting only the monomer emission, which is coming from the blue region. You can see here we are getting a single peak at near about 450 or 475, which is a blue fluorescent materials. But in case of ethylene diamine, we are getting two bands. One band is coming about 475 nanometer, and one sharp band is coming around 625 nanometer. So this is the mixture of two colors. One is complementary color, and this is the red color. So this in the case of ethylene diamine, we can see the emission spectrum is cover all the visible region from 400 to almost 700 nanometers. That is why we are getting the white light emission in the case of ethylene diamine, because in the case of ethylene diamine we are getting the white light, we are getting the J emission, and so one peak is coming from the monomer and another peak is coming from the J emission. That is why and we have calculated the CIE color coordinate, which is coming around 0.28 and 0.33, which is close to the perfect white light emitting coordinates, and color temperature we have calculated 8479 Kelvin. We have calculated the size and morphology of prepared graphene quantum dots, and we have found that this graphene quantum dots has just 8 nanometer of nano size and have the graphic nature, which is from HRT we can see there is a spacing. We have found the 0.35 nanometer, and their graphic nature was also confirmed by the XRD and Raman. We have found two bands, that is the graphic bands and disordered bands in the case of Raman spectra, which confirms the graphic nature of the graphene quantum dots. And XRD, which is from the XRD spectrum at the 2 theta, we have found the broad peak 0.33, 23.8, which corresponds to the interlayer spacing of 0.35, which is correlated with the HRT analysis. From HRT, we have calculated the interplanar spacing, that is 0.35 nanometer, and from the HRD, from XRD analysis, we have also calculated the interplanar spacing 0.33 to 0.35 nanometer, and 2 theta is 23.8. Next. We have also did the functionalization detailed XPS study to get the clear picture of the graphene quantum dots, and we have found that this graphene quantum dot is composed of carbon, of nitrogen, and oxygen, and they are well functionalized to ammonium cation and carbonyl group, carboxylic groups. Next. Then this white light emitting materials we have mixed it this white light emitting solution with PVA film polymer matrices. So we have found the perfect white light emission in the after mixing this this traffic quantum dot in PVA solution, and we have found perfect white light emitting under UV light excitation, and we have found the quantum yield is 0.52, which is good enough to the compare with the other reported method, and CI values 0.28 and 0.30. So the white light emitting material is only useful in the solid state. If you are achieving the white light emission in solution, it is not useful for the technology development. So we have used this material and we have tried to mix this material in the polymer matrix, which gives the perfect white light emission. So we have also seen that by changing the graphene quantum dot concentration, there is shift from blue to red, that is the J deviation. See, as at the concentration of graphene quantum dot is 21 microgram per mm, we have found the perfect white light coordinates, which is 0.28 and 0.33 with color coordinate 8479 Kelvin. But the concentration of this white light emitting in white light graphene quantum dots changes from 1.3 microgram per mm to 168 microgram per mm. There is shifting color coordinate from white to red because of J deviation. Next. This is the possible mechanism of J deviation. This is the synthetic representation of graphene sheets, which is functionalized with the ammonium cation, and these ammonium cations have tendency to form electrostatic interaction with carboxylate ion and hydrogen bond. So these two phenomena also suggest that this is the J deviation formation, because of J deviation formation only happen in the case when the molecule has electrostatic and hydrogen bonding interaction. Next. This J deviation studies have been further verified by the lifetime analysis, and we have found that the fluorescence lifetime of monomer is greater than the lifetime decay of JDA. So we have confirmed that proposed hypothesis by fluorescence lifetime and zeta potential measurement, because the zeta potential is also coming around 0, so which suggests that there is a formation of aggregates. There is no positive or negative charge are present in the graphene quantum dots because of the electrostatic and hydrogen bonding interaction. The zeta potential is coming almost 0. We have used this white light emitting materials. So this is the UV LEDs, which is excited, which is coming at 380 nanometer. Then we have coated this UV LED with PVA matrix, graphene quantum dots, and by applying the voltage of 3 volt, we can see the ultraviolet LEDs gives the white light emission, and we were able to distinguish all the colors. We can distinguish any colors only possible by the white light emission. If you want to distinguish all the colors in the presence of red color, not possible. Green, not possible. So you can able to distinguish red, green, blue, yellow, whatever in the case of white light emission. So here we can see that on illumination of white light emitting graphene quantum dot after coating in the UV LEDs, we were able to distinguish the yellow, blue, green, and red. In the second line of work, this is my PhD work, we have also prepared the white light emission from the mixture of pomegranate extract and its carbon nanoparticles, and this is the published in Journal of Material Chemistry C. So we have prepared the green emitting carbon nanomaterials from pomegranate extract by doing the hydrothermal treatment at 140 degrees centigrade for 24 hours, and then centrifuge we have found the yellow emitting carbon carbon nanomaterials, which gives the 11 millimeter of size and have carbon and oxygen elemental composition surface with carboxylic acid functional group functionalities in its surface. So we have prepared the green emitting carbon nanomaterials from pomegranate extract and we
यहाँ
have
सही है ना, यहाँ पर
characterized
सब
using the HR10 and XPS study. Next. We have also done the detailed optical properties of carbon nanoparticles and pomegranate extract. We have found that this